a big chunk of it over. Okay. So, all right. So I realize that I've taken quite a bit of time with the first part, a lot more than I wanted to. So let's move on quickly to the second. So about troubleshooting and roaming. And I need, another half an hour for the Wi-Fi 6 part of it. So let's get into this quickly, and I'm going to try to get some key points across. And if there are any doubts and all that stuff, we can have a separate discussion, with the groups if you want. Okay. So first of all, with roaming, there's some important things to understand, and that is that roaming decision is always based on the client. Okay. Ignore the words until 11ax. That's wrong. I have a must have a brain fart when I put that in. But no, roaming decision is always on the client, and roaming is always a break before make process. So break before make meaning that you have to disconnect before you connect. Now, obviously, there are some special clients out there, specialty clients out there that does has got the ability to do multiple connections simultaneously, but they are very specialized, and it's usually in the transportation industry space to do seamless roaming when they do train to track. So just think of it, Wi-Fi roaming is like marriage, right? You got to divorce before you remarry. Now in Philippines, I know you don't believe in divorce, but just as an analogy, you have to divorce unless and before you remarry. So it's that kind of an idea. Obviously, it doesn't apply to Muslims because they have the ability to have 4 wives all at once. Okay.
That's not always the
And
case.
what's also important is that clients may not make the right decision at the right time. Okay. And from an infrastructure perspective, vendors like us can only encourage roaming by nudging the clients using several techniques. And I will explain some of these techniques to help you, understand the process. And generally, what the clients go through would be to scan, connect, disconnect, scan, and connect. Okay. So there are things that affects roaming. The first of all is transmit power. Supported data rates is another. Okay. There are some protocol elements, 11V, BSS transition management request, 11K neighbor report, and 11R fast transition. Now 11R applies only to .1x SSID. Okay, it doesn't apply to open SSID. All right. Neighbor report and 11V BSS transition, they are applicable to all SSIDs. Okay. 11D, additional regulatory domain. This also impacts roaming. Okay, because it allows the AP to advertise the regulatory domain and therefore allow the clients to know which channels are in use, and makes it easier or more optimized for the clients to know, okay, I don't want to scan certain channels, I just bother with these set of channels. Okay. And 11H, likewise, DFS, okay, for radar avoidance, same thing. It allows the client to understand what channels can be avoided. Okay, so it doesn't bother scanning those channels. Okay. Now the settings. Okay, so this is in addition to what was covered earlier in the config recommendations. Then there's a bit of overlap. So 11DH, recommended, enable, default, disable. Okay, it provides proper regulatory info to clients. Client match by default is enabled, and therefore we want to keep it that way. And minimum data rates. And again, this was talked about when we were discussing the overheads in terms of the number of SSIDs. And one of the key reasons here is that we want to optimize our overheads, reduce our overheads by improving the airtime efficiency. And the way to do it is to raise the minimum data rates. Okay, you want to use 6, 9, or 12 and up. Okay. Now, how much do you reduce depends on the coverage area that you expect from that AP. So it also impacts your density of APs, number of APs you put. Okay. There are some other options. Local request threshold. I would recommend do not change it unless you open a case and tech prescribe it. Okay. You can play around with it, but be careful with it. Okay. And transmit power. Now, transmit power, the goal that I usually aim for is to have both the 2.4 signal and the 5 gig signal to be fairly balanced or equal. So you want to be able to, okay, when you go to any place and you do a scan, whether using Ekahau or just a regular Wi-Fi scanner, you want to see the 2.4 signal and the 5 gig signal coming out from the AP almost in a balanced way. The lobes are about the same size, same amplitude. Okay. There is a document which I provided in the link here that you can refer to for details of the roaming, behaviors, more deep dive in that. Okay, but over here, I'll just explain to you some of the mechanisms that is used to control clients. Okay, so in this case here, I have 3 APs and a client is connected to A, and what can happen is that A could send out a beacon management frame that tells the client there is this 11V field in there that says, okay, what is the transition candidate list? What are the list of APs that are nearby you, the client? And provide the BSS ID, which is the MAC address, provide the channel info. And what it allows the client to do is to know, okay, I have some other APs nearby. So, hey, I can make a decision. If I'm gonna, go to B, I know exactly what channel that B is operating on. Therefore, I do not waste time scanning the channel. And this way, A effectively pushes the client to join B. Okay, and this is a very fast, friendly, and certain method, but it depends on the client whether the client supports 11V or not. Okay, and if this is a screenshot of Aruba Central, and you will find it in Aruba Central. You actually can get the list of clients, and there is a field that tells what are the capabilities of this client. And you will see 11V listed in this case on some of the clients. So here is another 11V. So these clients are capable, and they will listen for these messages, and they may or may not act on the messages, but at least they are capable of receiving it. Okay. The second way, and this is very typical for most vendors to, do band steering, and that is using a de-authentication frame. So effectively, what we're doing is that the AP is disconnecting or kicking out the user, the client, by sending a de-authentication frame. So the client gets disconnected, okay? And the once it gets disconnected, it'll start scanning, okay? To determine, what are the nearby APs available. And in this case, it is possible that A will not respond to the probe request for the client because it's trying to prevent the client from connecting back. And that forces the client to see only probe requests, probe response from B and C, and therefore be able to connect to either one of them. Okay. This is a bit unfriendly. Okay. And it's, some clients react negatively to it. So this is sort of the other way, okay? The third method is through transmit power and minimum data rates. Now, every cell size is related or associated with a certain data rate. So when you have a low data rate at 1 Mbps, your cell size is very large, meaning that people can go far and connect. Okay, now as you reduce the data rate or enforce a certain limits on the data rate, that cell size, shrinks. So this is one way that we use to control the clients. Okay, if I want to get a higher data rate, I must be near to the AP. Okay, so we use this to control the client. So there are two ways to do it. Number one is to just change the transmit power. Okay, and this is an example. So if I have a data rate of 1 Mbps and I have a transmit power of 15 dB, if I reduce that transmit power, my cell size reduces. So the clients must be within this area in order to connect at a minimum data rate of 1. So that effectively brings down the cell size. Okay. The other way is to change the minimum data rate and increase it. So if I have a transmit power of 15 and minimum rate of 1, this is my cell size. Okay. If I increase that minimum data rate to 18, okay, that is going to reduce my cell size. Okay, it does not mean that the signal will stop there. The signal still goes out. Okay, and other devices can still receive signal from the AP, except that they cannot connect because they're too far away to hit or to maintain or sustain a data rate of 18 Mbps. Okay, so I always recommend using this method, and it is in our kind of a best practices guide. We try to maintain high data rates. Okay. However, there are some gotchas, and that is co-channel interference. Because we're keeping the transmit power high, we potentially generate co-channel interference. So that's why I talk about measuring co-channel interference, measuring how many lobes you get on the channel. Then you adjust your transmit power to reduce that co-channel. Then you set up your minimum data rate so that you achieve the distance that you require for your clients. Okay, so that is kind of the process. Okay, so how does this minimum data rate process work? So I have APs here, which I've drawn circles that shows the minimum data rate of 12 and data rate of 18 Mbps. Okay, for all the three APs, and the client is currently connected to A and is within 18. As it moves out to a boundary where you cannot sustain an 18 Mbps connection, what will happen is the AP will end up, kicking out the client, okay, because it is no longer able to support that minimum data rate of 18 Mbps. The client will end up having to scan, okay, and then realize that, okay, there are two options. One is C, okay, and it'll may try to connect to C. However, because it is in the 12 Mbps window, cannot maintain that minimum data rate of 18, C will not allow the connection. And then the client will be forced to connect to B, okay? So this management of the minimum data rate on the management frame and on the data frame is what is going to help you with limiting the cell size, enabling better connection with the client, and encouraging roaming. Okay, so these are the different techniques that are used. All right. Okay. And I'm going to go into the key stats quickly to show you what I typically look for when I look at the health of a deployment. Okay, there are two scenarios or deployments: the controller-based deployment and instant-based deployment. In both cases, there are information in there. They're slightly different, but it's a similar kind of thing that I try to look for, and it's kind of encompassed in this list here. Okay, now I'm going to give you a visual of it from a dashboard perspective. Okay, so one of the first things that I look for is the spread between 2.4 and 5 gig. Okay, and here the objective is to see, okay, do I have an install base that has a lot of 2.4, or do I have install base that are dual band, but I'm only getting very little 5 gig connections? And why is that? Okay, and obviously this depends on your deployment. It's not going to be a hard rule. If you have a lot of say outdoors, I'd expect to see more 2.4. But if I have a lot of indoors and APs with close high density, meaning APs are close together, I want to see, and I expect to see more 5 gig, okay, or balance. I mean, you're looking at almost, in some cases, 50-50, but I would prefer, if I can, to get more 5 gig than 2.4, okay? The second thing is, on the dashboard, in the controllers, we actually show the band channel width. And what I want to see here is, I want to make sure that on 2.4, I do not see 40 megahertz, because that will be an error in configuration. And on 5 gig, I do not want to see 80 megahertz. I want to see either 40 or 20. Okay. Next, I'll look at the frame types. And this is basically a comparison of the amount of multicast, broadcast, and unicast. Now, just bear in mind that for Wi-Fi, broadcast and multicast is bad. If you have a lot of broadcast and multicast traffic, it is not good for the health of your network. So you want to reduce that. Now, obviously, your deployment may not allow you because you may have IPTV that uses multicast. So you need to take into in consideration what is your applications. All right. In hospitality, I expect less multicast, more unicast. Okay. So in this scenario, I have a lot of multicast to the client, which means there's something in my network that is generating multicast. Okay, and I want to find out what that is. I want to limit it, or I want to tune my configuration to manage the multicast traffic. Okay, same thing from the client. A lot of multicast from the client. So I want to investigate who is generating the multicast traffic and why. Okay, frame rates is another one. Now you will notice that in the controller we will show light blue for low data rates, dark blue for high data rates. Okay, and in this case to the client, there's a lot of low data rates. And this is because of the multicast. Multicast goes out at a minimum data rate. In this case, either 6 for 5 gigahertz, 6 Mbps, or 1 Mbps for 2.4. And that is the reason why we want to increase or shift up that minimum data rate. Because otherwise, you're going to introduce a lot of overheads. Okay. Over on the section on from the clients to the AP, I have more high data rates, which is desirable. I want to see more high data rates, both directions. Okay, and if not, I want to investigate what is generating that low data rate and try to reduce that or eliminate that. Okay, frame drops is indicative of collisions. So the higher the frame drops you have, the more collisions you have. Okay, and this is something that you should already discover when you are in your site survey phase, testing for hidden nodes. Okay. Next will be low SNR clients. So this is where we want to see and reduce, right? I want to have fewer low SNR as possible. I cannot eliminate it. This is not possible because your deployment is not going to be physically consistent. Some areas you may have fewer APs because it's not important, and therefore you expect clients to connect from further, and the SNR will be lower. Okay, this is expected. So you just want to be sure that when you click on these APs that have low SNR, where are they? Are they in areas where you have plenty of APs? And if you have, then something is wrong. It points to the fact that your transmit signal, your signal is going too far, and users are connecting from far away. They're not connecting to the nearer AP. Okay, so this allows you to do some more fine tuning with the cell size. Okay. Client health is a little related to SNR, but it has got more composite metrics. So this is something you want to monitor, but you can't do anything to it specifically. In fact, it's actually a combination of other things like channel utilization. So which is next, okay, and the low SNR. So channel utilization on this side here is the list of APs that have high or experiencing high channel utilization. And this is where you want to narrow down to see which channels are these APs operating on, and what is it that's causing high channel utilization? Is it because of the number of users? Is it because of the environment where there are other, Wi-Fi transmitting, okay, on the same overlapping channels? Okay. Channel quality is related to channel busy and interference. Okay, so we want to have, again, fewer APs that are experiencing poor channel quality, and we want to know where they are in order to determine the environment around those APs. Why are they causing issues? Okay, all right. So when you have a situation, as I mentioned earlier, in site survey, that you can see that, oh, the AP in a room is covering like 3-4 rooms to the left and to the right, then when you deploy, you're likely going to see channel busy, a high number of APs with channel busy, high percentage in such a deployment. And that's going to tell you that, hey, you have too much co-channel interference. Okay, but my point is, I do not want us to wait till we are deployed and have all the users on it to discover it. And that is why at the site survey, that's the point where you collect the data to tell you if you're going to be experiencing this sort of channel utilization issues. Okay. All right. I have some exercises here, but I will not go through them. And these are kind of, based on real cases that happened before, where, you get information coming out bit by bit, slowly as you discover them. And, this exercise is really to stimulate discussion and to, exercise the thought process in terms of sharpening your troubleshooting skills. Okay. So yes,
Hello.
question. Mm-hmm.
Yeah. Where do we see these stats or information on Aruba Central?
Okay, so Aruba Central is slightly different. I don't have the screenshots for this. I will get back to you. I have come back to you. I have screenshots, but I've not put it on a slide like this. I've not done it in that way. Aruba Central actually is somewhat easier because there is AI insights, and those AI insights actually tell you a lot of this information in a dashboard that allows you to drill down to which APs are affected and which clients are affected. So in some ways, Aruba Central is a lot easier. Okay.
Okay. Yeah. Thank you.
Yeah. So just ping me separately on email so that I can show you some of those screenshots. I have them, but it's not in this deck.
Okay. Got it.
All right. Because I don't know who's speaking. Okay. So I will
Yeah.
not go through.
It's Philip. Yeah.
Yes,
TC. Philip from
Philip
Globe.
from.
Globe.
Okay, Globe. All right. Sorry. So just ping me on email. All right. Now, I'm not going to go through this exercise in full, but I just want to give you an idea, what is this kind of, I guess, typical things that we see when it comes to gas complaints. This is just a scenario from Singapore. Guests in the room gets disconnected from Wi-Fi for a short period of time, about twice a day. Okay. Consistently. The AP that's deployed is 11N 2.4 gig model only. 2.4 gig, meaning it's not a dual band AP. And the AP is located in the room next to the minibar. Okay. So with this three information, I want you guys to think about what comes to your mind. Okay. What are the possibilities? Okay. Now, if you have thoughts, you're free to share it, but I'm going to continue, okay? It happens to random rooms. There's no fixed rooms, okay? Okay. All right, so to me, when I get this sort of, what do you call it, information, there are a few things that I want to investigate. I want to investigate, how the channels are assigned. I want to investigate if there's any possible external interference. Okay. I want to understand which rooms they're coming from. Okay. The complaints are coming from, and therefore relate to those APs and what channel they're operating on. Okay. And it happens at specific times of the day, about 2 times or so, or 3 times. Okay. All right. And as I said, it's going to point me to certain things that I'm going to look for, like say, in this case, external interference, channel, what channels are in play in here. And what we discovered when I investigate this, is that I get high interference or transmission errors during those times, okay? And they happen on APs that are operating in channel 6. Okay, so the ultimately the root cause we found out was because of the minibar, and this happened with Western Singapore using Ruckus. There was interference on channel 6, and it is a non-Wi-Fi interference. It was Zigbee. Okay, so when the hotel does a inventory flush of the minibar, and they do that on certain times of the day, the Zigbee transmission actually overlaps with channel 6 and causes interference on channel 6, causing clients to get disconnected. Okay. So the resolution for this is that we block out channel 6, meaning remove it from the allowed channel list and use only channel 1 and 11, because these are in-room APs. All right, by using channel 1 and 11, we actually do not have any issues with co-channel interference, because the rooms have the walls that actually separate them, that allows us to mitigate co-channel interference. So we have fewer channels, in this case just 2, but it solved the problem. Okay, so this is just an example, and there are a few others that I have in here, but I'm not going to go through them all. Okay, there's Philippines, Malaysia, and Indonesia. So when you get the deck, just kind of go through them, and I guess think about it yourself, how you would troubleshoot it given the information that you have from the hotel. Okay. All right. Just a quick pause. Any questions? Because I have 30 minutes left. Okay. All good. Now let's move on to Wi-Fi 6, the new technology, the new, greatest, and latest, and most exciting and stuff. Okay. So Wi-Fi 6 or 802.11ax. So to understand this, we need to kind of look back a little bit on the evolution of Wi-Fi. Okay, so this little animation here shows you kind of the timeline and the kind of performance we're getting from the different standards that have come out. And Wi-Fi 6 is the 6th generation. Okay, and you'll notice that with Wi-Fi 6, we were hitting what's the speed? 9.6 gig. Okay, and if you're looking at the Wi-Fi 5, which is 11AC, that's 3.4 gig. Okay. So what is the rationale behind 11ax? In the previous standards, the focus had been on maximizing performance. However, with 11ax or Wi-Fi 6, the focus now shifts to maximizing efficiency. And that is where you see a lot of terms like HE coming in, high efficiency. Okay. High efficiency, the whole idea behind it is that the protocol itself, there are a lot of overheads and a lot of inefficiencies that we try to maximize. And the goal with maximizing efficiency here is to try to increase the average throughput per device in a dense deployment. And you saw earlier, with things like co-channel interference, with things like the number of devices on a single channel, each device is going to get little airtime because the airtime is shared among all the devices. So the throughput drops very quickly when you have a lot of users. And Wi-Fi 6 aims to increase that. Meaning, in a scenario where there are a lot of users, I want to be able to get much higher throughput per device. And the other thing is to try to enhance the operation in 2.4 and 5. The rationale behind it is 2.4 is limited in terms of channel. So how can we optimize that? How can we maximize that? 5 gig in some countries is also limited because the regulatory domain restricts, how much of a 5 gig you can use. So we want to find ways, or they want to find ways to, maximize or optimize the allowable or available frequencies of channels. The third goal is to improve power efficiency on client devices and improve outdoor performance. Okay, obviously that will also improve indoor performance. Okay, so these are the 4 kind of major goals, and the target improvement is given in a few areas. So we want to, or the Wi-Fi 6 is targeting to improve individual performance as well as system performance, and try to create new use cases. With individual performance, Wi-Fi 6 aim to look at increasing the data rates. So this is performance related in terms of speeds and feeds. and also battery life. Okay. As far as system performance is concerned, today most of the major issues lie with when you're deploying a lot of APs that are overlapping. So in a hotel, that is one example. There's so many APs that are overlapping. It impacts performance because of co-channel interference. So how do we improve that in such a deployment? And you're going to get more and more of this because in enterprise or any healthcare, retail, you're going to get a lot of APs that you need to deploy to support the density, right? Okay. And new use cases. How can we support IoT? How can we do better with outdoors? Okay. Right. So one of the key technology behind Wi-Fi 6 or 11AX is this term called OFDMA. Okay. And it stands for orthogonal frequency division multiple access. Big word. Okay. What is the difference with the old technology? Old technology is based on OFDM, which is orthogonal frequency division multiplexing. And how can you understand the difference? I'll use this animation or picture to help you figure that out. In OFDM, the old technology, the channel width, when you set up the SSID and the radio, you specify the channel width, be it 40, 80, or 20, or even 160. Okay, the entire channel width, okay, is used in a single transmission. So when the AP is going to send a packet out to one of the users here, it will send out that packet on the using the entire channel width. Okay, so imagine that channel width is like a truck, a big container truck. If you're using 160, it's a big container. If you're using 80, is a small container. 40 and it's even smaller container, and 20, gets smaller. But whatever it is, that container carries one packet. And that truck is going to make a journey from the AP to the client one at a time. So 3 different clients, that truck will have to make 3 trips. Or I have to have 3 trucks go one at a time, carrying packets of different sizes to those 3 clients. That is how OFDM works. Okay. If I were to display it in a more scientific view, this is a typical RF kind of a view where you have time scale and frequency scale, and the entire block here, the frequency, is a channel width. So the colors in there, the stripes in there, is actually a packet. One transmission at one time, carries one packet, goes to one client. Another packet goes to a different client. A third packet goes to a third client, and so on. And then it goes back to the second client. Individual clients get service at any one time. That is OFDM. What about Wi-Fi 6 using OFDMA? With Wi-Fi 6, what we do with the channel width is that we subdivide it, or we create subchannels, and we allocate different clients to different subchannels. So these subchannels are called resource units in Wi-Fi 6. And the smallest term is RU26. Okay, it's a technical term, but we call it RUs. In a single 20 megahertz channel, it is capable of fitting 9 subchannels, small RUs. And that means that we are now capable of actually sending transmission up to 9 recipients, 9 clients, all at once. Okay, so if you look at this animation, I'm going to carry 3 packets to 3 clients, and the truck will only just go once. Meaning the AP in a single transmission is able to deliver 3 packets to 3 different clients. So imagine if it is 9 clients and the packets are small enough to fit into the truck, which is 20 megahertz wide, then I can send to 9 clients all at once. Okay, so
only the AP is the 11AX, right? All these
no, the clients have to be 11AX too. And this
Okay.
works both ways. It works both ways actually. So from the clients to the AP uplink, the same technique is being used as well.
Mm, okay.
Okay. So it's interesting because it allows us to actually serve more users and lower the latency. Why? Because now the clients do not have to wait, right? Because one transmission, I can service multiple clients. So the latency of transmission between clients is no longer there. Whereas with the previous one, I have to wait for the transmission to one client to complete before I can do another client and a third client and a fourth client. And therefore, it means that the more clients I have, the longer they wait, right? So the latency increases. So the advantage of Wi-Fi 6 is that now we have the ability to deal with clients that are low data rates. Why is this so important? Low data rate is speed of transmission, so 1 Mbps. So imagine 1 Mbps is the speed of that truck, how slow it moves. If I have 300 Mbps, that truck is moving really fast. So if I'm going to have that truck moving slow, I want to deliver more packets. All right, so that in one trip, I service multiple clients. Okay. So it becomes suitable for low rate clients, and this is actually applicable to IoT devices. Why? Because IoT devices tend to be smaller in footprint. They have very simple chipsets with limited antennas, and therefore the data rate that is maximum data rate is lower than standard clients like our laptops or even our phones. And therefore, when it comes to a lot of IoT devices coming on the Wi-Fi network, if you have the traditional method, those IoT devices is going to slow down your network. It's going to bring down your network. But now with Wi-Fi 6, you do not have that worry as much anymore. Okay. And it works for uplink as well. So uplink, all the clients will actually transmit on their RUs, the center frequency, the sub-channel. And that gets combined, gets received by the AP, and the AP can decode the packets from different clients using the different sub-channels. Okay. And it increases the system capacity, all right, overall. So again, from a time frequency chart, you will see this is time. So sometimes it may use the entire channel to transmit one packet, but it now has the ability to combine packets for different users. So you see the dark gray, light blue, another gray, another light gray. This means that I could send this to multiple clients, different packet size. Okay, and the last stripe here with this blue, light gray, and dark gray, I can send different packets to different clients at one go. That is the advantage of Wi-Fi 6. How are these sub-channels divided? There's a possibility of mix and match. So this is a 20 megahertz signal channel visually, and how the different sub-channels are divided up. Okay, so this is going to give you a way of understanding, how those sub-channels are used, and you could divide them up differently with different packet size, and they don't have to be the same. It can be different combinations, okay? Different sizes of packets, all right? That's the interesting thing about Wi-Fi 6. So you get different combinations, all right? So you can send to multiple different users of different packet size. This is another view, again, a more scientific view of those sub-channels. So I'll, allow you guys can use this as a reference. I'm not going to go into detail. Okay. All right. So OFDMA is very powerful. Okay. Now, and that is the key technology behind Wi-Fi 6. Now, Wi-Fi 6 also has MU-MIMO. Now, MU-MIMO is not new. It was available in 11AC, Wi-Fi 5. Okay. But with Wi-Fi 6, it introduces MU-MIMO for both downlink and uplink. That makes it a difference. Okay. Now, MU-MIMO is a little different. Multi-user, okay, MIMO. In MIMO, we actually make use of transmit beamforming, which is a term that says I'm going to control the signal in such a way that it reaches to this client, in this case, like the one on the top here, the phone, such that it's getting my signal strong. But the other two clients at the bottom is getting my signal as very weak. So I'm shaping the signal, okay? And same thing, for the signal that is in red. Okay, I want to shape it so that my laptop gets it strong, but my phone and my iPad gets it weak. The red is very little in terms of propagation to those spaces there. Okay, so this is kind of hard to imagine, but I'll give you this chart that helps you understand it a little bit better. This is a chart of a 2 antenna system. So if I have 2 antennas and those antennas are like in the red dots there, okay, there is a way for me to control the signal coming from both the antennas such that it's going to result in this propagation pattern. And you will see the white area there is where the signal is strong. It's like a wave, so imagine water or a pool. You get a strong wave. So you're getting good signal where those white spots are. And then you're getting weak signal where the blue areas are. It's a dip in the amplitude. So the signal is weak or nothing. Okay, we call it nulls. So when you have the ability to do it in such a way that client 1 is in the area where the signal is high, and then client 2 is in an area where the signal is low, then you have shaped the beam in such a way that you're getting your packet or your signal to client 1, but not client 2. Okay, so this is effectively, transmit beamforming or shaping of the beam. And this allows us to control how that signal is going. So if you notice that the signal is going kind of more strong towards the right side, right half, but it's kind of weak on the left half. So if there are any clients on the left side, again, they're not going to receive signal. Okay, so by using the different antennas, and if I have more antennas, the better I can control it. I can shape the beam. That is how MU-MIMO works. Okay. Okay, but in order to do that, the AP needs to know where the users are in space. And to do that, they will send what they call a sounding frame. It's like a signal, well, not a signal, but a frame that is used more like a measurement. And then, the clients are supposed to report back, hey, I'm receiving this signal at this level, how much, what's the amplitude? It's going to tell the AP. And this will allow the AP to know how is the signal being received by all the clients, and therefore, know how to shape the signal if it needs to send it out to, these users. Okay. So that is MU-MIMO. Okay. Now, what about uplink? So in Wi-Fi 6, another key and important technique or feature is it introduces uplink resource scheduling. Now, for 20 over years, Wi-Fi had never done that before. Wi-Fi had been a contention-based protocol. Okay, it is uncoordinated. Okay, if you look at this picture of a traffic junction, and by the way, this looks like Manila. Okay, how people get around in Manila, right? Uncoordinated. There is no no traffic enforcer, and what happens? Everybody just try to contend. Okay, so this works well in a single AP scenario, but when you have a multiple clients connected to different APs, they're going to contend for the channel, and that is going to be a problem. Okay, all right. And in 11AX or Wi-Fi 6, it introduces resource scheduling. So in 11AX, the AP becomes the coordinator. The AP is the one that actually tells the client, you transmit now or you don't transmit. And this helps with high density. This helps with battery life. And that is the advantage of using AX or moving on to AX, because then you increase the capacity of the network. You prevent retransmission or collisions. Okay, so the picture on the left in the past, why we have collisions is exactly because it's a contention-based allocation. I mean, there's no coordination, so it's contention-based. I try. If I don't get it, I try again. Until I get it. Okay, and that's where collision comes in. But in 11AX, we mitigate this. How does AX do that? It does it with this thing called a trigger frame. Okay, by sending out a trigger frame to all the clients. Okay, it allows the AP to understand, okay, first of all, do you have anything to send? Okay. And if there is something to send, I can now trigger you, right? And in this case, I send another trigger frame to get the data from you. And I'm going to tell you which sub-channel you're going to use. Okay, so different client will have different sub-channel. And again, it allows multiple clients to simultaneously transmit. It also allows the AP to coordinate which clients will do first, which clients will do next. So using this trigger frame is very important, and it allows coordination of traffic, both actually in this case more impacting the uplink. And what that means is that we will not have hidden node issues when we come to 11AX. Okay. So this couple of slides I will skip over. It just shows the difference between MU, MIMO, and OFDMA. What are the different impact? Okay, so I will let you guys look through this at your own time when you get the slide deck. Okay, but this key message here is that they are complementary. They can be used together. Okay, and manufacturers will try to find ways to implement both simultaneously to maximize performance. Okay. More importantly, this is the chart that you want to understand, and this chart is about network capacity. Okay, network capacity is the total capacity of your AP versus the number of users that are connected to it. So at the bottom, you will see the client count, and this is the total capacity of the AP in throughput. Okay. So when you have few clients, the throughput is, well, if you have few clients, obviously you're not going to maximize it. As the number of clients increase, the total capacity goes up, but at some point it starts to come down. Why? Because there's so many overheads. More clients are contending, so there's a lot of overhead, collisions, retries, so the capacity, total capacity drops. Your individual user throughput will also drop even more because of the amount of overheads. Okay, but this is with OFDM or pre-Wi-Fi 6. With Wi-Fi 6, your total capacity actually, if you notice, does not go down as quickly. And therefore, the users, even though there are like 100 users there, overall, each of them is going to get more throughput. Okay, so the impact on the density of users is a lot less compared with before. Okay, that is the biggest change of the performance when it comes to Wi-Fi 6. Okay, lastly, there's this thing about BSS color. Now, BSS is basic service set, and Wi-Fi 6 introduces BSS color, and I want to quickly go through this. I have 10 minutes left, so I'm going to overrun a little bit. Okay, now we know that Wi-Fi uses CSMA-CA. That is carrier sense multiple access with collision avoidance. That is the way Wi-Fi works. This is listen before talk protocol I mentioned before. And when you have co-channel interference, it's going to impact performance. Okay, so these are the co-channel interference, things that you see when you run a Wi-Fi scanner. And as I mentioned, when you look at it, you want to count the number of loops. Right. In this case, I have 1, 2, 3, 4, 5. Yeah, over here 4, right, and over here 5 as well. Okay, so these are all going to be contributors to co-channel interference. Okay, and the logic behind CSMA CA is that every device, including the AP, if the AP or the device wish to transmit, it will have to check if the channel is busy. If the channel is busy, it will have to back off and wait and try again later. If the channel is not busy, then the device can transmit. That is the logic. Okay. So at what level do I consider busy? Today, most of the manufacturers have a fixed threshold. We call it a carrier sense threshold. That's at about -82. Okay. So when it is above -82, I will consider the channel as busy. Okay. So if I have this scenario where I have 4 APs, so 1, 2, 3, 4, and out of these 4 APs, 2 of them are on the same channel, channel 6, A1 and A4. And both these APs have clients associated with it, connected to it. And the way CSMA-CA works, it creates a problem where if the AP A1 is transmitting to the clients, any one of the clients, that signal can be heard by A4 because it's not very far apart. So when A4 hears that signal, it's going to ask, if A4 wants to send any transmission out to its own devices or own client, it's going to check if that channel is busy. And if that signal is strong enough above NAC 82, it's going to say, yes, that channel is busy. So what does it do? It'll wait. Okay. And that is exactly the problem that we saw when we do the design analysis of the APs in the corridor. The AP will be waiting for one another to be completing the transmission before it services its own clients. So that is what causes co-channel interference and performance issues. So how does Wi-Fi 6 solve it with BSS color? With BSS color, the AP, when it sends out the signal, is going to carry a bit, a color bit, we call it. That is going to indicate what cell or what color it is. So A1 would be color bit blue. A4 would be color bit 6. So that color bit in the beacon will allow the APs to differentiate itself from others. So when A1 is transmitting to any one of the clients, okay, that signal gets to A4. Now A4 is on the same channel as A1, but it's on a different color bit. So when it hears that blue signal, it's going to say, oh, it's not my cell. It's not my devices that are transmitting because we are all in red color. Our color bit is red. It's somebody else. Okay, now this is where it gets this interesting, right? So first it says, is it my cell? Is it red? It's not red, it's blue. I hear blue. The question is, how strong is that signal? Is it noisy enough for me to consider as impossible to transmit, right? And here is where I have to make a judgment. Is the noise threshold too high or too low? So if my noise threshold is NAC 67, and the signal that I'm getting from the blue is below that noise threshold, is weak signal from blue, okay? Then I have the ability to transmit to my devices while blue is transmitting. Okay, does this sound confusing? Well, let me show you the logic. If I wish to transmit, first I check if the signal is from my cell. If the signal is from my cell, I wait because it is my clients that are transmitting to me or another client transmitting to the AP. So I am the other client, I have to wait. Then the question is whether that signal is that I'm detecting is it very strong or not strong above a certain threshold. If it is very strong, I do not want to transmit at the same time because my receivers are not going to pick it up. So I'll wait. But if the signal is low enough that I can transmit to my receivers and they can receive it well, I'll go ahead and transmit. Okay, so all this sounds complicated, but Let me explain it with a simple example of a restaurant. Okay, so whatever you hear, if you didn't understand, this is the one you want to pay attention to. Okay, imagine in a restaurant, and we have all been there before, we know every table represents an AP with clients connected. Okay, so if you're seated on a table, you are either an AP or a client, and you're talking to your friends who are clients that are connected to an AP. Okay, and this environment would be equivalent to all the APs operating in the same channel. Why? Because you can hear every other table. So if you're at the table with your friends, you can hear others speaking because they're all on the same channel. Okay. And that is exactly the kind of scenario that we face when we have all the APs operating in the same channel, when you configure them on channel. The point here is that, are you able to speak to your friends on the same table, despite the noise from other tables? The answer is yes, provided that the noise from the other tables is not high enough to prevent your users or your friends on your table to hear you. Get a picture? So there is a certain threshold, and that threshold is dynamic. It's different for different tables. Okay, so if you have your grandfather on the same table, then you may have a problem. The noise may be too much for your grandfather to receive you well. So you have to, either get closer to your grandfather, or you have to talk louder so that your grandfather can hear. So that threshold may be different for this table where you have old folks listening, and a different table where you have younger folks. Okay, get the picture? So when we have the ability to talk to our friends on the same table, we are doing that transmission at the same time as other tables are doing their transmission. Okay. But if suddenly, one of the tables or many tables, gets too noisy, they talk real loud, then you find it impossible to talk to your friends on the same table. That is when the noise level is too high. So you cannot transmit at the same time or talk at the same time as the other tables, and you literally have to wait, or you have to leave the restaurant. Okay, so BSS color sort of is depicted by this kind of scenario. You're on the same table and you're speaking to one another. You can hear noise from others, but they're not on your table. They're a different cell, different color. Therefore, if you know that you can speak with your friends, loud enough that they can hear you, you go ahead to talk. Clear? So I hope this analogy helps you understand this BSS color thing, because it's a little complicated, I'd say. But the whole idea is encouraging spatial reuse and reducing the impact of co-channel interference, okay, as well as adjacent channel interference. Okay, so ultimately, there are some implications, and what these implications are is that 2.4 is back. We can leverage 2.4 and use it better. Okay, you potentially can also use wide channels like 80 megahertz, 160 megahertz. Okay, right, and Aruba has got AX aware client match that differentiates, and helps to move the AX clients to the AX APs, and enabling all these capabilities on the AX technology. Okay. Last bit is the target wake time that improves longer battery life, and this one I'm just quickly going to explain that with Wi-Fi 6. The AP actually negotiates sleep-wake schedule with the clients. And this allows the clients to go to sleep for longer. And the AP will actually use the trigger frame to wake up the client's individual user to transmit or receive. Okay, so it maximizes the sleep time for users and coordinates them, preventing collisions when the users wake up every now and then to try to check, okay, or transmit. So this is the other way that improves battery life, okay, up to 10 times. Okay, so that's significant. All right, now there are others, and we're hitting 1 o'clock. Now there are others that I'm not going to go through on this slide because we're running out of time. You can look at it at your own time when you receive it. They are not as significant in terms of impact, okay? And this table shows what are the benefits from 11 versus 11AC, okay? So again, I'll let you go through it at your own time, okay? Now, certification-wise, today Ruckus has only one model certified for Wi-Fi 6. Meraki has 0, and Aruba has 8. Okay, so Aruba is the only vendor that has all APs fully certified with Wi-Fi Alliance. Okay, now there are some key takeaways in terms of Wi-Fi 6 is that you will enjoy better throughput per station, per user in dense deployment. Okay, so you're gonna get much better user experience with density. Okay, now from a preparation perspective, you want to make sure that you get on AOS 8 because the Wi-Fi 6 models are supported only on AOS 8. Okay, you may also need to look at smart rate, the switch ports, because there is a potential that the traffic may exceed 1 gig. Okay. You also need to look at your PoE requirements because those APs will require higher power, BT power. Okay. Now, Wi-Fi 6 also introduces new security standards called WPA3 and Enhanced Open. And those are the things that you want to take advantage of in hospitality deployments. Okay. Right. So WPA3 introduces a new PSK, so to speak. We call it simultaneous authentication equals, and that is going to improve security. It also introduces enhanced open. This is with encryption. So today, the problem is that in hospitality deployments, we're using open networks and traffic is passing clear. And this is actually putting our users at risk. Okay, because anybody can sniff, okay, and hijack the transmission. However, with OWE, opportunistic wireless encryption, we actually provide encryption on an open network, okay, without having to key in any key. So you get the benefit of existing open networks without the complexity or the difficulty of getting people on it, and yet provide security. Okay. What does it all mean for hotels? The first thing is that now it allows you to connect more IoT devices. You can handle a lot more users, which means that your guest satisfaction will increase. And another thing is that once you put all these IoT devices on, you may suddenly find that, hey, your Wi-Fi becomes mission critical. You cannot allow any downtime or minimum downtime. Okay. So these are some implications from the whole introduction of Wi-Fi 6 and the ability to protect your guests with encryption on open SSIDs. Okay. So that is, in a nutshell, Wi-Fi 6. I know it's a lot to absorb, and sorry, I'm running a little bit over time. I want to open up for questions at this point.
Hi, TC.
Yes.
I'd like to know what are the benefits of deploying AX APs over the legacy devices, which are not AX yet.
Okay. So the benefits, I just highlighted a few. You get much better support for IoT, and you get much better handling of user density. So in your ballrooms, convention, high density areas, airports, Wi-Fi 6 is gonna serve you better.
So, I mean, even those and devices that are not Wi-Fi 6 capable yet.
So, well, the answer is that you will need Wi-Fi 6 capable clients to take advantage of it, but it's a chicken and egg problem, right? If you don't deploy Wi-Fi 6 APs, your client's eventually going to be Wi-Fi 6 capable, and at some point in time, somebody's going to take a first move. So obviously today we have very limited Wi-Fi 6 clients, but as more and more of the next generation phones come on, they will be Wi-Fi 6 capable. All right. So
So
we are at the transition moment.
okay, so meaning we cannot take advantage of the Wi-Fi 6 yet because of the client devices are not yet Wi-Fi 6 or just
To some
minimal,
extent,
right?
yeah, to some extent that is true. You will not see, huge improvement. Let's put it this way. At this point in time, although there will be some improvement, and that is in the context of the fact that if you have mostly 11 AC clients, for example, obviously they're not going to gain a lot of improvement. But as more and more of the 11AX clients come on board, don't forget that the airtime utilization for the 11AX clients will be better. So it gives more airtime now for the legacy clients. So you will see some improvement from that point of view. Okay.
Okay, because we're trying to convince management, for example, to move to Wi-Fi 6 deployment, but I would say
Yeah,
most
it's a
devices
chicken
now,
and egg problem. It's a chicken
yeah,
and egg problem. Yeah, but you'll find that it doesn't make sense to upgrade, for example, if you do an upgrade, to buy the legacy APs, because the 11AX price AP price is almost the same as the 11AC price.
Maybe TC, the question is it the right time now to upgrade from Wi-Fi 5 to Wi-Fi 6?
Actually, I would say yes, this is the right time, because the chipsets for the clients are now starting to come on. You see the new iPhone and the Samsung phones, they are Wi-Fi 6 capable, the S20
But
and the iPhone 11.
but how
So
far?
you're going to get more and more. You have to give a period of 3 years to ramp up, but it is going to happen. And the transition is the same as when we went through 11AC, right? There's wave one, there's wave two. It just takes, that 2 to 3 years for that ramp up to happen.
But how long? I mean, what
Mm.
in terms of the cost? Is it too far?
No, if you look at the pricing for AX versus AC, there is very little premium, very little difference. It's just not worth going back to the AC model. I'll be upfront with you. And most of the vendors are going to EOL the AC models when they start getting their AX models approved by Wi-Fi Alliance.
What?
maybe the cost of 11AX APs will go down, and maybe by next year, the next will
Yeah,
be
maybe
time to
the, the
deploy.
minute the minute you EOL the AC, your price for the AX will end up being adjusted. Yeah.
Okay. So in terms of its features and capabilities, how can we test those? Like for example,
Uh,
those
so
air
that's the
match,
tricky
this
that's the tricky thing.
right.
Testing 11AX, because like I said, 11AX is efficiency. So when you test, you have to have a certain test strategy, and that test strategy should focus on low data rates, meaning you want to get one by one clients, for example, or one by one devices, versus two by two and three by three devices, and look at how you can maximize the number of users on those. So it's more a density test than you would instead of a performance or throughput test, honestly. So
So
the goal is that I want to say, okay, if I add one user, this is my throughput. If I add 2 users, 3 users, 4 users, 10, 20 users, you will see for the traditional ones, the throughput drops. But with 11AX, you should see that as I add more and more users, my throughput per user remains fairly, well, it's not going to drop as much. That's how you would test.
um,
It's a
And it's
difficult
tough,
to test.
difficult to test.
right,
Yeah.
it's kind of difficult. So I'm thinking of you said an air match, this called BSS coloring, I'm pretty sure that those colors should be present on the controller, right? I mean,
Um,
is there a way for us to
so
at least see if this
uh,
user goes to this color, the other one? I know it's just a
yeah,
term, but um,
you
is there
would
a
do
way for
that
us to
through
verify those informations? Like, how can we
yes,
cross check it that we have an improvement on our performance? Let's say
right,
we
okay,
conduct a test on a strategic test.
mm,
It,
right, right.
for sure, you
So
have those kind of use cases, right?
yeah, I believe we have, and I mean it's just tricky because the amount of resources required to set up tests is going to be something not everybody can afford. You know what I mean? Because of the number of
Mhm.
clients that you need to be able to put in. And with regards to what you mentioned about the color bit, you would have to do a packet capture over the air to look at the color bit, and that's how you would, figure that, determine that. Now, from a configuration perspective, this is going to be lightly automated, meaning that you probably will not have an option to set the color bit for the cell. And I believe this is going to be done in the background by the operating system on the AP. Okay. But I am not sure at this point in time. I mean, all this is fairly new. I mean, we have 8.6, which is new, and I haven't even used 8.6 yet, and I don't even have many AXAPs that I can use to test that. I have only a 505 with me, 515 with me. Sorry. Okay. So yeah, I haven't come up to the point where we figure out how to do testing.
Yeah, because so far
So
what I see on web is just doing iPerf, speed test.
that is not the way to do it. I'd say it's just a waste of time. I would not even try to go there.
Right.
Yeah.
So I hope Aruba have those kind of strategic testing,
Yeah,
so we
we
can convince
probably will have.
management, so we can, if it's the time already to upgrade from Wi-Fi 5 to Wi-Fi 6, then we should have at least some cases to
Yep, yep.
justify the need.
We we will. In fact, we do have the kind of testing equipment that can generate multiple number of clients at different control environment, and we will be able to get reference comparison between the AX and the non-AX. In fact, earlier that chart on the network capacity, it came from our lab. Okay, so I would dig a little bit more about the test environments that we have, and what are the test strategies and test configurations and test results, and if we have that, we definitely want to share it with our partners. Okay,
Perfect.
yeah. Somebody asks, how many years do you think will future-proof clients wireless LAN Go 11AX now? Now, you need to understand that with Wi-Fi, the technology cycle has been 5 years, pretty much consistent 5 years. You look at the time period from A, B, G, N, AC wave 1, AC wave 2, and now AX, they're all 5-year span. So your technology cycle is approximately 5 years. Yes, you can go beyond that a little bit, but 5 years is the kind of ballpark number that you're looking at. So at this point, we are at that transition, okay, between AX to AC to AX. Okay. Any other questions? Okay, no. If not, then we will wrap up, and we've kind of overrun it about 15 minutes. Thank you all for your patience. I hope that you got something out of the training. I will send the link to the materials and the recordings. Now, today's recording is going to be partial, unfortunately, but I have the recording from my Hong Kong, which I can share that with you. So, for the Hong Kong partners, so you can review that for the first half, especially the best practices. And I will also have a survey link that I will need you to help me fill up, and provide some feedback, and hope that you guys get a good benefit out of this couple of days. Okay.
Yeah, thank you very much.
All
This
right.
was very
Thank
informational.
you. And yeah, if there's any other further questions, just get me on email. And yeah, you know how to reach me. And if not, get to our local team. Evan's always there. Red and Ryan's always there. Okay.
Yeah, we'll just go to Novaliches if needed.
Yeah, you can. If they let you in at the checkpoint, you're most welcome. You can have a little party at my house. I have some fundador here.
Oh,
uh,
I
nice.
guess
all
you
right.
will let Jeff fix your internet connection.
It's okay. I mean, there's nothing wrong with it most of the time, but occasionally, I get a little outage. All right.
I should have redundancy.
Okay. Hey, thank you guys, and have a nice day. Get a good lunch and stay safe. All right. Wash your hands.
Thank you, TC.
Thank you,
Thank
TC.
you. All
Thanks.
right.
Bye.
Bye bye.